Time is it? Oh, okay, it's 4 o'clock. All right, so let's go ahead and get started. All right, so we're going to finish differential geometry today, and then we're going to get into asymptotics and what it means to have an asymptotic expansion of a function. And we're going to solve the wave equation in the framework of asymptotics, asymptotic expansion for the electric field to derive the geometrical optics and the GTD terms. All right, so let's quickly recap what we did last time. We started talking about surfaces, and in this case, we had a surface parameterized by two variables, u and v, and a rectangular region in the parameter space, for example, in UV space, maps over to a two-dimensional surface now in R3. And each given point here will map over to some point in the R3 space. This one maybe maps over to here, and so forth, right? So now you have a parameterization of a surface in terms of two variables. But now, since it's a multivariate vector-valued function, it has partial derivatives, so two tangent vectors, Ru and Rv. Right? Differentiate your position vector with respect to u, gives you the tangent vector in the Ru direction along the line where v is some constant, right? So you hold v constant, you vary u, that traces out a line, you differentiate that position vector by holding v, constant, or differentiating with respect to u, and then you get the position vector, or sorry, tangent vector in the u direction. Same thing with the v direction. Okay, good. Now, we looked at some surfaces. Once we had two tangent vectors, we can define a normal, Ru crossed with Rv, and that gave us this normal here. All right. And then we started talking about curvature. How are we going to define curvature for a surface? Well, if we intersect our surface with a plane that's spanned by the tangent vector in a given direction, so t hat, some given tangent vector on the surface, and the normal. These two vectors span a plane, and if we intersect a surface with that plane, we can define a curve C, which is called the normal section curve. All right? So that curve C, we can use the formulae for the curvature of a curve, and what we find is we have just the formula for the curvature of a curve that we learned for space curves. But we have subscript C now to define that we're talking about the normal section curve, the planar curve C. All right, well, there can be a difference between the normal unit vector here. The normal for a curve is well-defined, right? The normal for a curve is well-defined, but the normal for a surface can be either up or down, for example. So this curvature for a curve is always positive, but the curvature for a surface in the given direction t could be positive or negative, right? Depending on whether or not the normal to the curve, the normal section curve, or the normal to the surface are parallel or anti-parallel. All right? And last time I had some error here, but this is the correct way, what I'm going to say right now. I originally had it right, and then I changed it when we were in the lecture, but the original thing was right. So n always points toward the source, right? Which is opposite of the wave vector. So here's the source, n is pointing toward the source, right? Here's the source, n is pointing toward the source. All right? If kappa is greater than 0, if this kappa, the surface kappa, is greater than 0, because only the surface kappa can be either positive or negative, if the curvature is positive, the wavefront is said to be divergent, which makes sense. If it's positive, the normal points back toward the source, and that's also equal to the normal to the curve. And the way that happens is if the curve is concave, I guess, toward the source, which would give you a diverging wavefront. If the source is transmitting, then the wavefront is diverging, right? So this is a divergent wavefront when the curvature of the surface is greater than 0. All right, and then opposite for when kappa is less than 0. All right, good. Then we talked about the radius of curvature, which is 1 over the curvature, and then we started talking about first and second fundamental forms. I added this notation here. So form here, the word form, refers to what's called a quadratic form. A quadratic form is a homogeneous quadratic equation where all terms are of degree 2, right? So, for example, okay, we'll get into that, but these arise when the function z equal to f of xy is defined on the plane at z equal to 0. For us, it's the tangent plane, right? So we define this kind of open quadratic second order approximation to a wavefront or a surface on a tangent plane here, right? The tangent plane to the surface. And so if the tip of this quadratic surface, for example, is at z equal to 0, and it's defined over the tangent plane, then f and its partial derivatives with respect to x and y vanish at z equal to 0. So, for example, if we have a full Taylor series expansion of the function z equal to f of xy, we have f of 0, 0, first partial derivative evaluated by x minus a, but we're talking about the expansion at 0, 0, because some surface here, right? So say some surface here, like this. We're talking about some point here, P, and we have a tangent plane over that point, and it has its own basis vectors, RU and RV, and we're defining this quadratic form over this tangent plane, right? So that means the tip of this quadratic form is at z equal to 0, if you will, or the origin of the coordinate system defined over the tangent plane with the normal vector as well. And okay, so that means we're doing the expansion around 0, 0, 0, right? So that means this x minus a normally would be x minus 0. Okay, so it's just fxx plus the partial derivative with respect to y times y, and then you have the second partial, the mixed partial, and the second partial in the y direction. However, we're defining this f of 0, 0, well, that's equal to 0, right? So this term goes to 0, and then the first derivative of the surface at z equal to 0, evaluated at 0, 0, 0, is also 0, and x is equal to 0 at that point, so these two terms go away as well. So you're left only with second order terms, higher degree terms. And that's called a quadratic form, like this. So this is basically the Taylor series expansion of this paraboloid that's defined in the tangent plane, all right? So when you see first fundamental form, we're talking about quadratic forms, all right? Okay, good. It's defined over the tangent plane with its axis as the normal vector and its tip at 0, 0. Good. And then we define the second fundamental form, and we derived the formulas to calculate these. So I added some extra words here on how to calculate these. This RU crossed RV is nothing but square root of EG minus F squared, right? And then here we say since RU dotted with n hat is equal to 0, because n is normal to the tangent plane and RU lives in the tangent plane, then what we can do is we can differentiate this with respect to u, right? So let me see, what did I do here? Yeah, so RUU dotted with n. Yeah, okay, so this is the product rule on this, right? If you use the product rule on this equality here, then you get this equality. So g times f prime plus f times g prime. All right. But we know that, okay, so then we can move this term to the other side, and what we find is that RU dotted with NU is equal to negative RUU dotted with N. So these RUs minus RU dotted with N is here, right? So you can replace that with RU dotted with, I'm sorry. So it's this term that you see here, right? So you can replace that with RUU dotted with N. And that's what we've done. RU dotted with N. N is RU cross RV. But then you have to divide out its magnitude, right? To make N a normal unit vector. And the magnitude is nothing but square root of EG minus F squared. Okay, good. So that's how those formulas you get those, how you get those formulas. We did an example, and then we got to this point, I think, right? Okay. So let's talk about the principal curvatures. So at any point P on a surface, the curvature we saw, which of the surface kappa of T hat, is a function of the direction of that tangent vector, right? So as I rotate the tangent vector, we saw in this example here, as we rotate the tangent vector here from a line with RU when alpha is equal to 0 to a line with RV when alpha is equal to 90, the curvature goes from, 1 over A, the radius of the cylinder, to 0, right? Because if we're pointed along RV, the curvature is 0. The surface is flat in that direction. All right? So the curvature depends on the tangent vector. And a knowledge of kappa of T hat for all T hat in the tangent plane determines the bending of the surface in the neighborhood of P. Okay. So as T revolves in the tangent plane, a pair of orthogonal directions exist for which kappa take on minimum and maximum values. All right? That means that the surface only has 2 degrees of freedom. If there's a maximum and a minimum direction of curvature, then you can express all other curvature direction, the curvature in all other directions in terms of those 2 degrees of freedom. All right? All right, so those directions, those orthogonal directions of which kappa takes on maximum and minimum values, we're going to call those principal directions. And they're represented by the unit vectors E1 and E2 hat. These are very important, all right? Okay, the 2 extreme values of kappa are called the principal curvatures, and they're denoted by kappa 1 and kappa 2, all right? So, real quick, what are the, just by observation, what are the principal curvatures and principal directions of this cylinder? What does the principal curvature mean, right? It's what? What's that?
Oh, well, I'm just thinking that 2 curvatures seem like 1 over A and 0.
Very good. Yeah. So that's right. So it's 1 over A is the maximum curvature, right? The direction of maximum, the maximum curvature is 1 over A. The minimum curvature is obviously 0. So the 2 principal directions are, in this case, RU and RV, right? Principal directions, RU and RV for the cylinder, and the principal curvatures, 1 over A and 0. So the maximum and minimum curvature directions, right? Okay, good. So that implies it's only 2 degrees of freedom in kappa, and we'll see how we utilize that fact. Since we can write any vector in the tangent plane T, right, as a weighted linear combination of the basis vectors that span that plane, the tangent plane, with some coefficients T1 and T2, then the curvature can be written in the following form. So kappa of T, we're going to define it as the second fundamental form divided by the first fundamental form. And we know the second fundamental form is negative dr dotted with dn divided by dr dotted with dr, right? Those are the definitions of the first and second fundamental forms, okay? And we derived what the dr dotted with dn was. This is the second fundamental form, and this is the first fundamental form. So it's a ratio of sort of quadratic forms. And in terms of, okay, so look here. Here's t hat, which is dr d sigma, right? We know that. The tangent vector is the derivative of the position vector with respect to its parameter, right? And if it's a unit vector t hat, it's a unit speed curve, then it's parameterized in terms of its arc length. All right. Well, dr can be written as ru du plus rv dv. How is that? Okay. Well, think about this. It's the total differential, right? So if I have dr du, well, that's equal to ru, right? dr dv is, whoops, rv, right? So say I move the du to the right-hand side and the dv, then dr is ru du, right? But a total change in dr is not only due to the displacement in the u direction, but also the displacement in the v direction, right? Okay, good. So d sigma is still there. Now, so now we have du by d sigma, and we know what that is. We can call that T1, right? Because T1 here, if we call T1 du d sigma, then du is equal to T1 d sigma. So we'll need that fact soon, all right? And then RV could be dv by d sigma, and we get this expression here. All right, so now, why did we derive these from our coefficients du over d sigma being equal to T1? Because if everywhere we see du in this expression, we can replace with T1 d sigma. All right, and so forth. Then you get this expression here. So now, this expression tells you the curvature in the direction of t hat parameterized in this way for any direction of t hats, right? In terms of the coefficients of that representation of t hat. All right, now what we can do is we want to find these minimum and max, or maximum and minimum extremums of the curvature, right? So how do we do that? We differentiate our kappa with respect to T1 and set that equal to 0, which means because we're looking for the extremum, right? So partial kappa T1, T2 with respect to partial T1, we set that result equal to 0. Same thing with respect to T2, all right? In doing that, you derive these two expressions. We can write these in matrix form like this. So this is a set of linear two equations, two unknowns, for example, and we want to calculate the determinant of the coefficient matrix in order to get a non-trivial solution. And what we find is this quadratic equation here, all right? So okay, so this is the quadratic equation that results from setting the determinant of this coefficient matrix equal to 0, right? Now, but it's in terms of these two quantities called the mean curvature and the Gaussian curvature. All right, so we'll define that on the next slide. So basically, if we calculate the mean curvature and the Gaussian curvature, then we can use this quadratic equation, find its two solutions. It's a quadratic equation, and those two solutions are kappa 1 and kappa 2. So what is meant by the mean curvature and Gaussian curvature? The mean curvature here is exactly what it sounds like. It's the mean between the two curvatures, right? Kappa 1 plus kappa 2 divided by 2. And if you solve this quadratic equation in terms of the quadratic forms, if you go back to here and use the notations here, then what you obtain is this expression for the mean curvature. The Gaussian curvature is the product of the two principal curvatures, all right? So, and if you go back to the definition of first and second fundamental form, you'll find that's EG minus F squared over EG minus F squared. And we'll use this in this lecture a lot today, all right? So once you have kappa G and kappa M, you can use the quadratic equation to find the two roots, which are the principal curvatures, kappa 1 and kappa 2. Yeah? Okay, so you guys are learning like a crash course on differential geometry, but we need this for geometrical optics, right? So I'll make sure to highlight what's important for you guys to learn, what's important for you to understand, what's important for you to remember when we get to the geometrical optics part and all that, right? So, but this is a lot of differential geometry in 3 lectures for you guys. But at the end, we just need what's called the curvature matrix, really. We have to understand how to construct the curvature matrix and what it represents for surfaces that we might be reflecting electromagnetic waves from, like a subreflector or main reflector, and also for wavefronts, right? And we're going to tie the curvature of the wavefront to its amplitude. And that's the main takeaway from all of this, okay? And you'll get a homework to try this Wednesday, I think. All right, good. Okay, so now that we found what kappa 1 and kappa 2 are, we go back to our system of equations, we substitute in kappa 1 and kappa 2, and then we can solve for the T1 and T2, which give you those kappa 1 and kappa 2, right? That gives you, so what does it sound like we're doing? And we're going to solve it that way later on. So we're solving a homogeneous system of equations, 2 equations and 2 unknowns for 2 particular values, and then we're going to substitute those back into the system of equations to find 2 principal vectors, right? The eigenvalue, eigenvector type of thing. Okay, good. If you do all of that and you work out the algebra, then you end up with these 2 principal directions. In terms of a couple of quantities, gamma 1, L, alpha, beta, gamma 2. And all those expressions are here. Here's alpha, beta, gamma 1, and gamma 2. Okay, this should not be L. This should be, I think, 1 probably. Those are 1s, all right? They shouldn't even be there really, if it's just 1. Okay? One observation is the principal directions are orthogonal, which is good. And okay, good. So what do we notice here? All we have to do, we'll do a couple of examples during this lecture, to calculate all of these results, that all of these characteristics of surfaces and wavefronts based on their curvatures and directions and all of that, it all comes down to 6 quantities is all you have to calculate, all right? The 6 quantities are the coefficients of the first and second fundamental forms. Little e, little f, little g, calculate big E, big F, big G, then you can calculate everything in terms of them. So here, everything is in terms of these coefficients, GF and E, right? All of this is. Everything comes down to these parameters. So, and these parameters are easy to get. You just have to differentiate your parameterization, first and second derivatives. And then you can calculate what these E, F, and G's are, and then you can calculate everything from them. All right, so it's not that difficult.
K1 and K2 will be known as well.
K1 and K2 are in terms of, okay, yeah, so they're in terms of Km and Kg, and then you can, or kappa M and kappa G, and then you calculate kappa 1 and 2 based on kappa M and kappa G, but kappa M and kappa G are a function of E, F, and G, right? Lowercase and uppercase. All right, there are special points when the curvature kappa 1 is equal to kappa 2, and at all point, or at some point P, so at all directions, the curvature is the same then, right? If kappa 1 is equal to kappa 2 at some point P, then everywhere you look, all directions have the same curvature, like a sphere. All points of a sphere are umbilic points. These are called umbilic points, all right? Umbilic. All right? Good. Okay, so we can also take an arbitrary tangent vector t at P, and we can parameterize it in terms of the principal directions now. So we choose a new basis here, right? Before, what basis did we use? We used RU and RV as the basis, right? Here, we used RU and RV as the basis before, but now we're going to choose the principal bases. So these are now, t hat's now in terms of the principal bases. Why are the principal bases useful? Because they're orthogonal. So then we have just this parameterization, cosine alpha E1 plus sine alpha E2. So then we can express the curvature in this basis using as the following expression. Still a function of the first and second fundamental form parameters, E, F, and G. Okay, if we differentiate this expression with respect to alpha, we can determine the two extreme values of kappa now, because now this is technically a function of alpha, right? So this is really kappa as a function of alpha, right? All right, and those two become this and this. So you get a alpha pi over 2 and alpha equal to 0, you get these two solutions, yeah? So substituting these back into the curvature formula shows that the curvature in arbitrary direction can be expressed in terms of the principal curvatures and this kind of sinusoidal interpolation. Yeah? Okay. All right. Okay. This is all going to become very useful and clear when we get to starting to describe these.
So the principal direction have to be necessarily orthogonal?
Principal directions are orthogonal, yeah.
Did you say that principal directions represent the max and minimum curvature too?
The directions of maximum minimum curvature, yes.
So the maximum direction is always orthogonal to the minimum direction?
That's correct. There's a theorem that it reminds me of called wobbly table theorem, I think. Have you ever been to a restaurant and you're at a table and it has like it rocks like that? Look up this theorem. It's really cool. If you're out with your significant other, then you can really impress them with this. So if the table rocks, because of this curvature theorem, and I think it's based kind of on that, or it reminds me of it, you can rotate the table. There's always, it's guaranteed, it's proven that there's always some angle where it doesn't rock anymore. It balances. Yeah, so you can rotate the table. All right, very cool. All right, so let's do an example. Well, let's use the ellipsoid shown on the right. Here's the parameterization. Okay, so there was a mistake. I fixed it on the earlier slides, but not here. And it's fixed here. But this should be sine, and this should be sine, right? And this should be cosine. Depends on where you reference your angle, your elevation angle. All right, so make that correction. Okay, but this is correct here. So this is it. This is the steps you need to take to calculate all of these quantities that you'll need to solve electromagnetic diffraction problems using geometrical optics or geometrical theory of diffraction. So you start with your parameterization of your surface, right? Then you differentiate with respect to u and v, get the first partial derivatives, then the second partial derivatives, and this should be vv. Man, okay. Yeah, that should be vv, sorry. That there's that mistake as well. And once you have all those derivatives, you have everything you need to calculate big EF and G and little EF and G, right? So this should be V, right? If you do this calculation, remember what is E? Capital E, do you remember? We go back. Capital E is RU dotted with RU, right? Here are the formulas. So once you have the first derivatives, you take the dot products, you get capital EF and G. All right. Then, so that's here. You get these three. These are the dot products between, RU, RV, and then RV. All right. Then, to find little EF and G, that's the second fundamental form. And there, you use these formulas, the second derivatives and the first derivatives is all you need there. So once you calculate capital EF and G, and you have the second derivative, RUU already, and you have the first derivative, RU and RV, you take the cross product, you can calculate little EF and G. All right? So what you get is these results here. All right? Good. Now that you have EF and G, capital N, lowercase, everything else falls out of that. So now step 3, calculate the mean and Gaussian curvature. These are in terms of these parameters, right? So you calculate those, you get these results here. And calculate the principal curvatures. Once you have kappa M and kappa G, you can calculate kappa 1 and kappa 2. Yeah? All right, then once you have kappa 1 and kappa 2, you can calculate the principal directions because you need alpha, beta, gamma 1, and gamma 2. Yeah? So here's alpha and beta, gamma 1 and gamma 2, and they're all in terms of kappa 1, kappa 2, and EF and G, lowercase and uppercase. And, of course, alpha and beta, but you calculate those first. Yeah? Good. Let's do a specific numerical example. This is in general, right? We haven't chosen a point P. But if we choose a specific example, let's choose the ellipse that has the parameterization coefficients of A equal to 2, B equal to square root of 2, and C equal to 1. And let's choose the point P to be where U and V equal to pi over 4, which gives these Cartesian components. Where do you get those? If you go back to the parameterization and you plug in pi over 4 for U and V, then here you'll get X, Y, and Z. All right? Okay, good. If you do that specific example, then you get RU and RV here. You get E, F, and G, and little e, little f, and little g like that. And here's the point P, by the way, in the actual parameterization. And then you get kappa M, kappa G, kappa 1, 2. All right? We got to remember these values that we've calculated, especially this kappa 1 and kappa 2. Remember this for sure for later in the lecture. And remember this is an analytic result. Then also we calculate alpha, beta, gamma 1, and gamma 2, get these specific values for the particular point and the particular parameterization. And then you can calculate E1, you get these specific vectors here, and E2, you get this one here. So remember E2, E1, and kappa 1, 2. We'll come back and refresh you later. All right, good. All right, yeah? So am I going too fast? That's the other thing. You won't know if you understand it. I mean, you're kind of following along for sure, but you won't know if you understand or have questions until you go and try it on your homework. That's why homework is super important, right? So that's when you can refer back to this. If you have questions, you can ask. But, okay, this point U here is the umbilic point, right? So at that particular point, the curvature is the same in this direction as it is in that direction, yeah? All right, no questions so far, huh? All right, good. All right, you're all experts, good. All right, curvature matrix. So there's a way to do all of this compactly and succinctly, and we're going to use this notation for what we're going to do, what we're going to use differential geometry for, which is to solve problems in EM diffraction and scattering. So for a curvature matrix, on a surface sigma, so we call the surface as sigma, there is a normal n at each point, right? As n moves, oh my goodness, as n moves away from that point in arbitrary direction, its variation follows the bending of sigma in that direction. For example, look here. Here's a cylinder. We have some tangent plane at some point P here, and there's two tangent vectors that span the tangent plane that we can express other vectors in terms of. as bases are u and rv, which is the first derivative, first partial with respect to u, and then the first partial with respect to v of the parameterization position vector r, right? All right. Then the normal to that surface is n, okay, at that point P. If we track how the normal vector changes as we move away from P, so normally it's, you know, in the neighborhood of P, we're talking about differential geometry here, but I've kind of exaggerated it here, right? So n is there at first, but if you move to this point, you get that, then here, then there, right? So the normal vector variation, the change in the normal vector follows the bending of the surface. And we're going to use that to derive formulas for the curvature of a surface. All right? Of course, we've already defined curvature of a surface. How did we define that? Just give you guys a little recap. What did we do? We know one thing, the curvature of a curve is well defined, right? So how do we use that to define the curvature of a surface?
Like take another plane with the normal plane, you get a curve.
Very good. So first off, first observation, the curvature of a surface depends on what direction you're talking about, right? So to fix that direction, we take a tangent vector in a particular direction, which is in the tangent plane, right? That tangent vector t hat can be expressed as a weighted combination of ru and rv, for example, and the normal vector. So now we have two vectors, a tangent t hat and a normal n hat, and those two vectors span a plane. We intersect that plane with the surface that cuts, that's called a principal normal section, and it's called a normal section. And that intersection develops a curve called the principal curve, or a normal section curve, right? All right? Now we know how to define the curvature of a curve, and we use that concept. And then we can rotate this tangent vector and calculate the curvature in all different directions. There are two particular directions, E1 and E2, the principal directions, of which the curvature takes on a maximum and minimum value. That means the surface curvature, kappa of t hat, has only 2 degrees of freedom, kappa 1 and kappa 2, and all other curvatures should be expressible in terms of some kind of interpolation between those two curvatures, right? That's what we saw. All right, but now, instead of using this sort of t hat and n hat normal section curve that we're going to define the curvature in terms of in a particular direction, which we also express as a ratio of the first and second fundamental forms, right? Instead of doing that, we're going to track the normal, all right? Which is kind of similar. All right, good. So, following this idea, we may introduce a quantity measuring the variation of n hat at each point on sigma. How do we do that? We go back to the same thing we always do. Take some kind of dot product relationship and differentiate it. So if we differentiate n dotted with n hat equal to 1, with respect to u, we get this expression, right? So nu is the partial derivative of n hat with respect to u, dotted with n, that equals 0. What does that tell us? What does this expression tell us here? Very good. The dot product is 0. So the derivative of n with respect to u is orthogonal to n. So where does it lie? What's orthogonal to n? Tangent plane. Very good. So the derivative of n lies in the tangent plane. See? So we should have probably called this nv. That would have been better. So nv and this one nv, right? Or no. Sorry, not that. I want to call this dnv. Or dn, but okay, fine. So, and nv and nu are orthogonal to n, which means they lie in the tangent plane. So what does that look like? If I have n at the point, 0 in the tangent plane, n had a v, for example, and then I move away a slight distance in the v direction, then I'll get a new vector, which is n of u plus delta v, or n of v plus delta v. If we take the derivative, if we calculate what the derivative of that vector n hat is, which is just n of v plus delta v minus n of v divided by delta v, well, delta v goes to 0, then we find this vector, right? Which is basically, remember you subtract the vectors, n of v hat plus delta v minus n of v. based on the formula for derivatives. That vector is orthogonal to n by these expressions here, and therefore lies in the tangent plane. All right? Okay, very good. If a vector lies in the tangent plane, then what does that mean? We can express it in terms of the base vectors which span that space, right? That plane. So we're going to write it like this. Negative nu is q11, some coefficient, multiplied by ru, plus q12 times rv. We're just expressing this vector, which lies in the tangent plane, in terms of these basis vectors, all right? And the coefficients are called q11, q12 for now. Same thing with nv. We can write that succinctly if we define this curvature matrix here as q11, q12, q21, q22 in this form here, okay? Where this nu and nv are the components of nu, the xyz components of nu, which means you take partial n, partial u, and we dot it with x, then with y, then with z, right? And then same thing with the v's here. Yeah?
What's that -%?
The negative, we'll see the negative, what it represents. What to think about it. You could probably define it the other way.
RU are RV are orthogonal Q1 and Q1 to 0.
Yeah, very good. That's right. No. If RU and RV are orthogonal, then not necessarily, right? If you displace in a direction which is not along U or not along V, then you might pick up these off diagonals, right?
They're orthogonal always, no?
RU and RV, no, definitely not, right? Remember,
So how we expand a vector in terms of like two not orthogonal vectors?
oh, very good. So here, in order to express any arbitrary vector in terms of two basis vectors, if you have these two vectors that span a plane, they only need to be linearly independent. They don't have to be orthogonal, right? So bases don't have to be orthonormal or orthogonal. They need to be linearly independent. As long as you have two linearly independent vectors, then you can describe any other vector in terms of those two linearly independent base vectors, if we're talking about a plane, right? So if they are orthogonal, which one of these quantities would be 0? F. So F measures the orthogonality of your RU and RV, right? Very good. Good question. Very good. Okay. So yeah. So you can write it like that, right? So what's the deal with the curvature matrix? Why are we introducing it? Is it useful? We're going to find that we can calculate these quantities and recalculate everything about the surface, principal directions, minimum and maximum curvature, Gaussian mean curvature, in terms of these matrix entries. And what's really useful is that the determinant and the trace of this matrix give you the mean and the Gaussian curvature, and then, or 1/2 of the mean curvature. And then we're going to express the change in amplitude of the electric field along a given ray to the Gaussian curvature of the wavefront. And the Gaussian curvature you calculate from the curvature matrix associated with the wavefront. So we'll see all that, all right? So everything compactly notated using these curvature matrices. So let's go back in and re-express everything we already derived in terms of the curvature matrix entries, yeah? So we have formulas for the explicit calculations of the curvature matrix Q. We need to develop those. So to do this, we introduce the first and second fundamental matrices, I, or 1 and 2, right? So 1 is the matrix of all the first fundamental form coefficients, capital E, capital F, and capital G. Here are the definitions for capital E, capital F, and capital G in the matrix. And we can express that in terms of this dot product or multiplication of two matrices, right? Same thing as all the dot products. Okay, good. Second fundamental form, same thing. We have a negative sign out front. That negative sign out front comes from our definition of the second fundamental form, I think. I think there was a minus sign. Yeah, there's a minus sign in this definition. That's where the minus sign comes from. Yeah? Is it clear? Okay. Good. All right. Here. All right. So we calculate these first and second fundamental forms. All right. Okay. Now, what are we going to do? Multiply both sides of this expression in terms of the curvature matrix by RU/RV. What does that do? That allows us to isolate the Q, because here we have this expression, Q2 is equal to Q into 1, right? If you go back, here, this thing is here, so we have this is kind of, if we multiply, all right, so, okay, remember this, right? If we go to the next slide. If we multiply the right-hand side, oh, here it is, the same equation. If we multiply this by RU/RV, then we end up constructing this on the right-hand side of Q, and that's nothing but 1. And on the left-hand side, we construct this, which is nothing but 2. So we get 2 equal to Q into 1, right? Good. Now we can take the inverse of I, or 1 rather, and we can solve for Q directly. So Q now is going to be in terms of 2 and 1, and 2 and 1 are in terms of EFG, right? So if you solve this product here, and you match up the entries of the matrix that results, upper left is Q11, and then lower right is Q22, and so forth, you get these expressions for the curvature matrices. All right? Good. Good. So now we can calculate the entries of the curvature matrix directly. So given the, and we're going to do an example, given the parameterization of the surface, then immediately we can calculate the derivatives of the parameterization. Then we can calculate E, F, and G, capital and lowercase. Then we can get all the entries of the curvature matrix. All right? And then it's very easy to calculate these principal directions and these curvatures, minimum, maximum, by doing eigenvector and eigenfunction analysis, or eigenvalue analysis of that matrix. All right, so once Q is found at a point P for a given surface, we may calculate its principal curvatures and directions at a point P, at the point P. Remember previously we found these as these expressions here, all right? Now if you look at these expressions and then you look at these quantities, then what you'll find is that 1/2 the trace of Q, which is equal to 1/2 kappa 1 plus kappa 2 is the mean curvature kappa M. And the determinant of Q is equal to the Gaussian curvature kappa G. All right, so what is the determinant of Q? That's Q11, Q22 minus Q12, Q21. If you calculate that with these expressions here, what you'll get is kappa 1 times kappa 2. All right? You'll get this expression here, basically. All right. So here's a theorem. If A is an n by n matrix, then the sum of the n eigenvalues of A is the trace of A, and the product of the n eigenvalues is the determinant of A, right? And we just said that, we just calculated that the determinant of A is the product of the eigenvalues, product of the n eigenvalues is the determinant, and the sum of the n eigenvalues is the trace. And we just said the trace is equal to this. That means that kappa 1 and kappa 2 are the eigenvalues of the curvature matrix. All right? So that makes the curvature matrix pretty useful, yeah? Okay. So now we can find the eigenvectors. What we have to do is diagonalize the curvature matrix, right? So the curvature matrix right now has all 4 entries. Whenever you diagonalize a matrix, what does diagonalization of a matrix means? It means this, right? If you find these matrices D, or this matrix D, and you multiply Q by D inverse, and on the left, and by Q by D on the right, then you'll diagonalize the matrix. The result is a diagonal matrix. All right? So, okay. So since the eigenvalues are the principal curvature, then the eigenvectors will be the principal directions when the matrix is diagonalized. So let's denote the two eigenvectors of Q as D1 and D2. These are the notations. So the two eigenvectors. We have a Q matrix. We found its eigenvalues. Now we want to find its eigenvectors. There's many ways to do that, right? But if you diagonalize the matrix, then immediately the matrices that you found to do the diagonalization are the eigenvectors, all right? So the first eigenvector, D1, satisfies this equation, which is nothing but AX equal to lambda X, right? Where kappa 1 we know is the eigenvalue. The second one, D2, satisfies this equation, yeah? Good. So if we solve more explicitly these equations here, what we'll find is this expression here. The ratio of D21 by D11 and the ratio of D12 by D22, which gives you a way to calculate what the entries of these eigenvectors are. All right? We'll do an example. So doing that, we end up diagonalizing the matrix, and the diagonal contains the eigenvalues now, and by using this matrix D. So D inverse QD. Standard linear algebra way to diagonalize a matrix. All right, and D here is the matrix made by juxtaposing the two eigenvectors as column vectors. Yeah? All right. Now, once we have this matrix D, if we multiply by RU, RV transposed, then we'll end up getting the principal directions. So these are the eigenvectors of that matrix, but they're not the principal directions yet. The principal directions are three-dimensional quantities. These eigenvectors are two-dimensional quantities, D1 and D2, right? So to get the principal directions, we need to multiply by RU, RV, the inverse of D. And we'll do an example. All right. So more explicitly, E1 and E2 are in terms of these quantities, and we have alpha, beta in terms of the Q matrix entries now, right? So now we can calculate everything in terms of the Q matrices. All right. All right, so I want to get into this really quick. I might skip this, but there's a way to view this thing called the Gauss map. So what is the Gauss map? The Gauss map basically takes all of the, oh no. It takes all of these normal vectors here on a surface, and it maps them over to a unit sphere. In this case, it's a two-dimensional cut of that, right? So, for example, for here, okay, so here's a parameter space, right? It lives in R2, and we have some map which takes us from the parameter space over to the actual parameterized geometry in Euclidean space, R3, using this vector here, RU and V, right? That's the map. Very good. And we said that the derivative of that map, the derivative of the parameterizations give you the tangent vectors RU and RV, right? Okay, now, we also defined another map. We said the derivative of the normal vector, we just said the derivative of the normal vector. So, first off, this plane is called the tangent plane to the surface S at the point P. All right, that's how you read that. But anyway, we said the derivative of the normal vector, dn, also lies in the tangent plane, right? So dn's also in the tangent plane. But if we make a map called the Gauss map, where we take this normal vector and we map it over to the unit sphere, so it becomes like a radius on this unit sphere, as n varies over the surface S, then this vector here, which is a unit vector, n hat, as acting as a radius to that sphere, will also vary, right? And as I vary this normal vector around the neighborhood of point P on the surface S, then I'm going to trace out a sort of surface area patch on the unit sphere, right? So, for example, if I move this normal vector here, and then in this direction as well, then I might trace out some kind of area of that unit sphere, all right? And the big thing that Gauss realized is that because this tangent plane here is orthogonal to the normal, and this normal is in the same direction as this normal by the Gauss map, this tangent plane to the unit sphere is exactly parallel to this tangent plane, and they are the same tangent plane. Which means this map dn is a linear map. It maps you from the tangent plane on the surface technically back to itself, right? Now, if you have a linear map, a linear transformation in terms of a matrix, which you apply that matrix to some, you do a linear transformation, apply it to some vector, you get a new vector, for example, right? The determinant of that linear transformation matrix tells you how it distorts areas, how that map distorts areas, right? So that's linked directly to the curvature. So don't get hung up on this geometric interpretation, not important for us, but this is really where it comes from. So the Gaussian curvature is the determinant of this map, which is a matrix, which is the ratio of these first and second fundamental forms. Because this is a composition map, right? You go first here, then there. So if you differentiate this, you can say that that's the ratio of this map divided by the one that takes you composite, first and then R, right? Or first R, then N. All right. We could talk about this more if you want. But instead, let's do an example, make these things a little bit more clear. All right? Okay. Let's go back to that ellipsoid. We calculated all the same stuff already, right? This is the same slide as before. We needed the parameterization and all its derivatives and these parameters. So nothing's changed by using the curvature matrix approach rather than using the previous approach, right? So we still need E, F, and G at this point. Now we go here. So step 3 is to calculate the curvature matrix now. So we have E, F, and G. We calculate Q1, Q12, Q21, and Q22. Form the matrix, right? Now, okay, so, all right, so we need to calculate what these entries are, right? In terms of analytically. So in order to simplify this, let's go back to, here we have E, right? This E here has a big old denominator, yeah? So the denominator, wait, let's go back here. Well, the denominator we're going to call D, right? So to simplify the notation. All right, that means then E is minus ABC over D, right? Because here we had ABC minus ABC divided by what we're now calling D, right? Okay. So that's what E is. And then F we can also express in terms of, F is 0, and then G in terms of D as well. All right, good. Now, we need to calculate the denominator first. EG minus F squared, they all have that, right? So let's calculate that. First, we calculate E times G. We can do that because here we have E and G is here and here, right? So we just multiply those two out. We get this, right? And then we calculate F squared. Then we subtract the 2, and we find that we get this compact form, right? Of course, D is some long square root, but D squared sine squared of U. All right? So the denominator is a D squared sine squared of U. All right. Now let's calculate the mean curvature and Gaussian curvature, which is 1/2 the trace of Q. And we know that the trace of Q is can be found like this. So the trace of Q is Q11 plus Q22 times 1/2, right? Okay, so if we add these two together, you get this expression here, right? And since we know little f is equal to 0, it reduces to this expression here. And then we know what EG minus F squared is, and we know what little e and capital G and all these numerators are. If you substitute those in, you get this expression here, okay? But we still need to calculate this quantity. So this quantity is given by this calculation. At the end, you get this expression here. All right? Okay. Good. Now, that means that the mean curvature can be expressed in this following way if you plug everything back in. All right? Gaussian curvature is the determinant of Q, which is this quantity here. If you do all of that, what you'll find is that it reduces to this determinant of, what is that? EG minus F squared. Let's go back to, okay, remember what, where do we introduce that? Here. 1 is capital EF G, right? What is the determinant of this matrix? EG. Very good. What is the determinant of 2? Right? So now, look here. Here we have, no, it's here. Here we have EG minus F squared, little EG minus F squared, and then capital EG minus F squared. So that's the determinant of 2 divided by the determinant of 1, right? So that means a Gaussian curvature is equal to the determinant of 2 minus the determinant of 1, or divided by the determinant of 1. And if you go back here, the determinant of 2 is the this map, and the determinant of 1 is sort of this map right here. So if you ratio those two, you get the Gaussian curvature, right? So don't worry about that interpretation just yet. But it's a way to tie it back together, right? Okay, good. So you get this for the Gaussian curvature, all right? Now, let's go back to XYZ coordinates. All we have to do is we have to note that from the parameterization, x is equal to a sine, so x is equal to a sine u cosine v. This is y and this is z, right? So knowing those, we can go back to here and we can calculate d in terms of x, y, and z now, which is this. So we've introduced the XYZ coordinates, the Cartesian coordinates for this rather than the parameterized u and v. All right, then we can calculate kappa m and kappa g in terms of the d squared here, right? The d squared is there, and it's also here, right? So now we have it in terms of x, y, z. Now kappa m has x, y, and z, and kappa g has x, y, z. Now we can calculate the principal directions, or principal curvature, and the principal radii of curvature. All right? All this is, you're going to do this 1,000 times when you solve these problems in geometrical optics and GTD. Yes?
And when we're solving these problems, are we gonna like get to these like analytical expressions for these things, or are we gonna increment like a certain amount, like numerically calculate like the derivatives, find the values that way?
No, you're going to do exactly what we're doing here, right? You're going to calculate the curvature matrix at a given point, P, right? And then you can take the determinant of that, and you're going to find then the principal directions from those eigenvalues. And then from there, you're going to express, we're going to talk about rays and surfaces carried by those rays, called the incident ray pencil. Then you need to express the surface that you're reflecting from in terms of its own curvature matrix, Q. Then you have to interact this curvature matrix associated with the wavefront, incident wavefront, with the curvature matrix associated with the surface to find what the reflected radii of curvature are, and the reflected Q matrix. And then from the reflected Q matrix, you can take the determinant of that at two different points and ratio it to find the amplitude variation along a ray. We'll get to all that, but you're going to need to do all this stuff, right? All right. So let's do it numerically instead. Here's some code to do it numerically, yeah? So we calculate RU and RV. This is at a particular point P, point that we used in the previous example. We calculated RU and RV there when I told you guys to remember what we did here, right? So we have, for the particular numerical example, we had RU and RV here. And then we calculated this kappa 1, 2, and then these eigenvectors, or these principal directions, right? So we can do it all numerically in code. So here's the RU and RV. Here's the RU and RV. And here's little e, little f, little g, capital E, capital F, and capital G at that point P for the ellipsoid. Now we can construct the curvature matrix. Then we can call this function in MATLAB called Eig, which gives you the eigenvalues and the eigenvectors of that matrix, right? And then we can calculate the principal directions as the inverse of that eigenvector matrix multiplied by RU and RV. And then if we want the actual principal directions, they have to be normalized. So this just normalizes them to unit vectors. What do we find when we do that? We find these are the eigenvalues, and these match exactly with what we calculated analytically. And these are the eigenvector, or principal directions, and those match exactly with the analytic results. So if you write a computer program to launch rays through lenses, or launch rays to reflect off of subreflectors for like dual reflector analysis, then you probably follow this approach, yeah? Numerically calculate all these quantities. Okay, that's it. One more thing, we got to approximate surfaces. Super important that you guys understand this, because all of our geometrical optics formulations are going to be framed in this framework here, all right? So approximating a surface. We saw how to approximate curves before, right? Remember when we saw the curves, we had first, second, and third order approximations as here, right? And we kept either first order, second order was in plane, so it only had kappa and sigma, right? Third order came up out of the plane, so it's not a planar curve anymore, so it has torsion, so we needed the torsion, right? From the Ferret-Serret. Okay, Same thing with surfaces now. We need to learn how to do that. What are we going to do? We're going to do a Taylor series expansion over around some point on a surface, right? So in EM diffraction problems, there are typically two types of surfaces involved. Hold on one second. This thing looks like it's dead. So let me change the batteries on this real quick. If they have any here. Yeah, they do. All right, sorry, 1 second. Okay. We're almost done with differential geometry. This is the last thing we're going to learn in it, all right? Then we'll get to some fun Maxwell equations and electromagnetics again. All right, batteries are updated now. Okay, good. So in EM diffraction problems, there are typically two types of surfaces involved. One, a PEC surface sigma where an EM field is to be reflected or diffracted, and two, a wavefront W of a ray pencil. All right, so here's a conducting surface. The normal to that surface always points toward the source, right? The source is way over here, but that's the direction of the normal. The only normal can either be inward or outward, right? Okay, we have an incident wave. It's going to reflect off this surface sigma, means conducting surface, right? All right, or we have a wavefront W from some source. There are rays emanating out of this wavefront, and each ray carries a differential piece of the surface that represents the wavefront. Differential piece of the wavefront, all right? Along with it. All right, since we are often only interested in local geometrical properties of sigma or W at a point O, right? We're only interested locally, differentially around a given ray, what the surface is doing. Rather than using the exact representation of the surface, we may use a quadratic approximation based on a Taylor expansion. So at the point O, let us introduce a set of right-handed orthonormal base vectors. Sigma 1, sigma 2, sigma. All right? Okay, so this should probably be sigma hat. So the third one, we don't, okay, so you're going to see why we don't use a notation 3 for the third one, because it's a function of the first two. We'll see that, all right? But sigma hat is the normal. In the examples to the right, sigma hat is plus n for the example surface, so it's plus n here. These are in the same direction. And sigma hat equals to minus n for the wavefront because of how we define the normals to these surfaces to point, right? Because so here's the convention. N hat always points toward the source, and sigma hat always points toward the incident field of the direction of propagation of the ray pencil. So sigma hat always points toward the incident field for a reflecting surface, or it always points in the direction of propagation for a wavefront. But we know that n hat points opposite to the direction of propagation for a diverging wavefront, for it points toward the source all the time. And so that's the two conventions, all right? So consider a point P on sigma in the neighborhood of O. The position vector R of P in reference to O can now be written in this way. Let's write it like this. Sigma 1, so we have three base vectors now. We have sigma 1, sigma 2, and sigma. Sigma points in the normal direction. So sigma 1 and sigma 2 kind of take the place of RU and RV. And these coefficients, sigma 1 and sigma 2, are the coefficients of those. Sigma describes, the lowercase sigma describes capital sigma locally, right? So sigma is the height, this surface. This surface is called sigma. So here's sigma, the height of a point P on the surface S, which we're going to approximate locally around the point O using a Taylor series, is a function of sigma 1 and sigma 2, right? So it's like Z equals to F of X and Y, right? This surface we can call Z. So that means this is like sigma, the surface. Remember, capital sigma is the actual surface. Lowercase sigma is the Taylor approximation of the surface, is equal to, you know, some sigma, I guess, of sigma 1 and sigma 2, right? Okay, good. All right. So let's represent R by this Taylor expansion. Let's expand R in terms of Taylor expansion. Now it's sigma 1 and sigma 2 instead of U and V. But sigma 1 kind of takes the place of U, and sigma 2 kind of takes the place of V. And we have the first derivative, R. Remember, the subscript on R means partial derivative with respect to. So this is like RU, but this is R sigma 1 multiplied by sigma 1 plus R sigma 2 multiplied by sigma 2. What happened to the constant term?
This is for the plane if we want parameterize tangent plane, right?
No, so, okay, so I must be going too fast. You guys gotta slow me down.
So
All right.
we said sigma one and sigma two are orthogonal, right?
Sigma 1 and sigma 2 are base vectors. Now, so instead of, normally we expressed some kind of surface, the tangent plane in terms of sigma or RU and RV, right? But now we're saying we're going to use a Taylor series approximation to the surface, capital sigma, locally around some point O. And we're going to create a second order Taylor expansion for that surface in this basis, sigma 1 and sigma 2. Yeah, they could be orthogonal, right? So the surface sigma, lowercase sigma now, which is the approximation, has its z, or sigma,
That's 0.
as a function of sigma 1 and sigma 2, which is the coordinates in the x. This is like z equal to f of xy, but it's sigma equal to sigma of sigma 1 and sigma 2. So what happened to the constant term in our Taylor expansion?
0.
Yeah, why?
To sigma equal to 0.
Well, we're doing the expansion about what point?
Because it's centered at the.
It's centered at the origin, right? And we're doing the expansion about 0, 0. So there's no constant term, right? Okay, then we have the first derivative of sigma 1 plus the first derivative in terms of sigma 2 times sigma 2. And then we have the second order terms, right? Okay, so r of sigma 1, what is that? That's the derivative of r with respect to sigma 1. But our r now based on, our r is based on this kind of parameterization instead. So that's going to give us the derivative with respect to sigma of this becomes, and evaluated at sigma 1 equal to 0, sigma 2 equal to 0, because we're doing the expansion about the point 0, 0. If you differentiate this with respect to sigma 1, then you just get sigma 1 hat. If you differentiate this with respect to sigma 1, you get 0 because there's no sigma 1. And it's constant with respect to sigma 1. If you differentiate this with respect to sigma 1, you get sigma multiplied. And remember, sigma is a function of sigma 1 and sigma 2. And if we look down here, we can find what that sigma is. We take r, and we dot it with sigma hat, right? Because let's go back to this, the r, for any point on the surface locally, so any point on this surface locally has this representation. In terms of these bases, right? These are the bases. So if I want to find what sigma is, then I just take sigma dotted with, sigma hat dotted with r. That's going to give me, sigma dotted with sigma 1 plus sigma dotted with sigma 2 plus sigma dotted with sigma times sigma, right? And what happens? Sigma dotted with sigma 1, orthogonal. Sigma dotted with sigma 2, orthogonal. Sigma dotted with sigma is nothing but 1, and then you get sigma. All right? So we go back here. R dotted with sigma gives us sigma, and that ends up being, so now, that ends up being this, right? So you can calculate this because you can express, so R of sigma, okay, I'll show you how to get to that. But this expansion here so we're differentiating this expansion. So here's sigma, right? We're differentiating with respect to sigma 1 up here. So we get sigma, and then the derivative of this with respect to sigma 1, we get 2e times sigma 1 squared, right? But there's 1/2, cancels. So we get e times sigma 1. And then we have 2f sigma 1, but then there's the 1/2 here. So you get sigma 2 rather, because we're differentiating with respect to sigma 1. And this goes to 0 because it's not a function of sigma 1. All right, evaluate all that at 0, you get this. So the only thing I'm trying to say is that the derivative with respect to sigma 1 is nothing but sigma 1, and we expect that, right? Sigma 1 is the tangent vector in the tangent plane that we're expressing this Taylor expansion or quadratic approximation of the surface capital sigma in terms of. If this was RU, then we'd expect, so that would be the derivative with respect to u. That lies in the tangent plane, right? So the sigma 1's in the tangent plane. That's all that's supposed to gather from that. All right, so let's go to here. Now, r of sigma 1's in the tangent plane. If we take the dot product with sigma, we should get 0. Same with r of sigma 2 is in the tangent plane. All right. Therefore, if we take So now what we can do is take the dot product with the normal on each side, and we get these expressions. So we can express this in terms of capital E, little f, and little g. All right. Okay. All right. So at the point O, we can start to calculate some of these things. R of sigma 1 we said is sigma 1. We know what E is. E is equal to R of sigma 1 dotted with sigma 1. So if R of sigma 1 is equal to sigma 1, then this calculation is nothing but sigma 1 dotted with sigma 1, which is equal to 1. So R of sigma 1 is equal to 1. Or no, E is equal to 1, rather. Sorry. Capital G is equal to 1, and F is equal to 0 because sigma 1 and sigma 2 are orthogonal. So if we go to our formulas for the curvature matrices and use these numbers for E, F, and G, then we'll find the curvature matrix to be like this. And therefore, sigma now can be written in terms of these, because normally it was written in terms of E, F, and G, but now we can replace that with Q11, Q21, and Q22, and we get this. We're going to use that a lot in geometrical optics, all right? Because we're only interested in the local surface, the surface locally around a ray. So we're going to express it in terms of this. So I suggest you go back in and we'll revisit this next lecture, but make sure that that's kind of clear, all right? This is, sigma is the Taylor approximation of the capital sigma surface, the whole surface locally, as around some point O, and it's in terms of the curvature matrix of that surface. All right? Okay. It's valid for small sigma 1 and sigma 2. Quadratic approximation. All right. If sigma 1 and sigma 2 are in the principal directions, then you get this. You just get a diagonal matrix. Q11 is equal to kappa 1, and Q22 equal to kappa 2, because we're in the eigenbasis now, right? Whenever you're in the eigenbasis, then your matrix becomes diagonal, right? So then we can express sigma in this form if we have it. And then that allows you to make interpretations of what does it mean when you have Gaussian curvature greater than 0 with both the kappas negative. Then that means you get sort of this ellipsoidal surface here, right? If kappa g is less than 0, so the Gaussian curvature is the product of the two curvatures. If it's less than 0, then that means one of the curvatures had to be negative and the other one was positive. Then you get this saddle point, right? Negative Gaussian curvature means that one principal curvature is negative and the other is positive. That's the only way you get a negative product. If they're both, if you get Gaussian curvature positive, there are two ways that can happen. Either they're both negative or they're both positive, but in either way you would get this kind of surface that is doubly curved in the same direction. Then, if you have kappa g equal to 0, Gaussian curvature, one of the principal curvatures had to be 0, like a cylinder, right? At this point, this looks like a cylinder. This direction it has curvature, but in this direction, locally, it does not, right? Good. All right, so next lecture, we're going to get into asymptotic expansions. But that means we are completely done with differential geometry. So you guys got a crash course in that, right? Curvature matrix is all you need to. So what are the takeaways? We need to parameterize the surface. Once we know its parameterization, we calculate its first and second partials. Then we can calculate little e, little f, little g, capital E, capital F, capital G. From there, we can calculate curvature matrix, Q11, Q12, Q21, Q22. Then we can take the trace and the determinant to find the Gaussian and mean curvature. And from there, we can use a quadratic formula to find the principal curvatures. And we can find the principal directions, all right? Principal directions are useful because they're the sort of the basis, the natural basis you want to use to get a diagonal curvature matrix. Diagonal curvature matrix is very useful because if I have a wavefront and I know its radii of curvature in the principal directions, it's a diagonal matrix, 1 over kappa 1, 1 over kappa 2 in the two diagonals, then I can evolve that along a ray as far as I want and calculate the new curvature matrix by using the new radii in those directions, right? But we need to be in the principal basis for that. All right, I know it's mathematics and we like electromagnetics, right? So we'll get to that. We'll get back to that very soon. Next lecture. And then we'll start to do cool things with this stuff, all right? All right, any questions? All right, very good. You get a homework on Wednesday. If you need help with your office, the office hours are now after class. If you need help, come up to my office. All right? And then I'll help you out with your homework. And then you can also email me anytime. And then you'll get a new homework on Wednesday when your other homework's due on this differential geometry. All right, good. See you guys.